This is geometry lesson 8.5. We're going to be looking at the areas of quadrilaterals, which remember are four-sided shapes. So we're going to look at some specific four-sided shapes like a trapezoid and a parallelogram, and then also some general ones that have some specific properties. So all of these formulas that we're going to use for our quadrilaterals, they're all derived from our triangle formula. So taking these shapes, breaking them into triangles and also rectangles, and then basically combining all of that information to come up with the formula. But we're not going to dive that deep. We're just going to look at the formulas themselves and how do we use them and how do we sometimes find some missing information when it's not given to us right off the bat. So we are going to start with trapezoids. This should seem like a familiar formula. This is not the first time you've ever seen it. So the area of a trapezoid equals half. So here's your 1/2, the product of its altitude, which we can call the height. All right, and the height of a trapezoid goes from base 1 to base 2. Remember, your bases are your parallel sides of a trapezoid. Two parallel sides make it a trapezoid. So the height has to go from base 1 to base 2 at 90 degrees, right? We wouldn't measure a height diagonally. That's not how tall it is. So from base 1 to base 2, even if this is spun sideways, you look for the two parallel sides, and the height could still potentially go from side to side if we spin this. Okay, but it has to go from base 1 to base 2, 90 degrees to be the altitude or the height. Okay, and then you're multiplying that times your bases added together. So similar to our triangle formula, 1/2 base times height, but now we have two bases that we need to add together first, and then multiply times the height and take half. And that can be done in any order, except for the addition. We know that inside parentheses comes first with our order of operations. So you could multiply 1/2 times the height, but then you would need to add these bases before you multiply all of that together. Okay, so add the bases and then complete your multiplication in any order that you like. So real basic one for here for number 1. We're only given the information that we need. So again, area equals 1/2 times the height times your bases added together. So my bases are my parallel sides. Okay, they're not given to us here, but we're shown a 90 and a 90. And the only way that's going to happen is if these are parallel. So I know these are my bases, and 6 is the distance between my two bases. They could have given you information out here and called this, say, 10 or whatever, to try and confuse you. You got to know not to use that. You're going to take the two parallel sides, plug it in for base 1, base 2, and then you're going to take the distance between them, again, which hits at 90 degrees, as your height. So plugging this all in first, height is 6. And base 1 plus base 2, I'm just going to drop them in here right now. The order that you put them in, you could say 9 plus 5 or 5 plus 9. Doesn't matter because we're adding them together. So first step technically is to complete the inside of parentheses. So you're going to add those together. That's 14. You can plug it all in your calculator, or you can, if you're doing it mentally, you can just take half of this number or half of this number. Or you can multiply these both together and take half at the end. The order of multiplication does not matter. So basically, half of 6 is 3, and then 3 times 14 is 42. All right, so that's your basic trapezoid area problem. So let's look at one that's going to take a little more thinking. All right, so we are going to compute the area of R, S, and M. So R to S to N to M, and of course back to R. So that trapezoid up top, that's what we're looking at here. They're telling you that RS, all of this up here, is 10. That's one of the bases. Here's your two parallel sides. Okay, so one of the bases is 10. We're going to be eventually plugging into this formula, base 1 plus base 2, because we do have a trapezoid, two parallel sides. So far, we can grab this height as well. They tell you that PQ hits at 90 degrees, the distance from a base to a base. That's my height of 4. One of my bases is 10. So all I'm missing is my other base from M to N, and I should look for it up here. But in this case, they're not going to give that to me. I'm going to have to go find it. So PQ, they told you, is 4, and QT is also 4. That doesn't help me yet. And then the area of triangle MNT, this triangle down here at the bottom, this triangle, that area is 10. And so they want you to compute the area of the trapezoid. In order to do that, I need the distance from M to N because that's the second base. And so since they've given you information about this triangle, you're going to have to use that to kind of work backwards and find that. So the area of a triangle, remember, is 1/2 base times height. So let's take a look at what they've given us. They've actually given us the area. So area is 10. They haven't given me the base. The base is one of the sides. But we know that this is going to hit at 90 degrees here. That's the height of the triangle. So the height is 4. We're going to leave base alone. And we're going to plug 4 in for the height. Now we have enough information. The only variable left here is b. So algebraically, we can work through this and figure out what b is. B will be the length of mn, which then I can come up here and plug in to help me solve for the area of that trapezoid. So there's lots of different ways to run your algebra in this equation. What I would do is take half of 4. Remember, this is all multiplication. You can do that in any order. So I'm going to take half of 4. So this becomes a 2, and I still have b. And now it looks very simple. Divide by 2. So I get 5. B equals 5. And in this case, the height is hitting the base at 90 degrees, which means MN is equal to 5. If the base of the triangle is 5, then MN is 5. So now I can go ahead and take that information, knowing that all of this right here is 5, and plug that in. Again, my height was 4 of the trapezoid, and then my bases were 10 and 5. So 1/2 times 4 times, add those together, 15. Half of 4 is 2 times 15. The area is 30. All right, to the back. All right, we're going to take a look at parallelograms. Area of a parallelogram is even simpler. It's just base times height, just like a rectangle. Should make sense because it basically is a rectangle just without the 90-degree angles. And so in a rectangle, we actually use the sides like length times width. That's how come you sometimes see that called length times width and not base times height. In a parallelogram, we cannot do that because we don't actually use the side that's on an angle now because it's not 90. Just like a trapezoid, the height has to be measured from base to base at 90 degrees. So there could be a height that goes from this parallel side to this parallel side, right? You've got two sets of bases. So one of these bases times this height would give you the same answer. Okay, so they can give it to you either way. We're not adding our bases together here. It is just a parallelogram, so it is just base times height to figure this out. All right, so real basic here. You just need to keep these straight. A lot of people, once we've done a trapezoid formula, now want to go ahead and use that here for a parallelogram, but it works a little bit differently. So area equals, I like to switch this up. I always call it base times height. Again, the order of multiplication doesn't matter, so I can switch it, not a big deal. So we're not adding these together here. It's just base times height. It's just going to be 15 times the height of 6. Notice they've given you these outside ones to confuse you. You have to make sure you pull the right numbers. So it is just 15 times 6. All right, and then 15 times 6 is 90. And you're done. So very easy. It's just multiplying two things together. If they had given you the area and then one of those, either the base or the height, you could work your way backwards through that as well. Just make sure you're not pulling the sides. Always look, the key is your 90 degrees. The height or the altitude of a shape is always going to hit the base at 90 degrees. So that's what you should be looking for. Okay, and then the very last formula we're going to look at is for quadrilaterals that have perpendicular diagonals. So I've got this four-sided shape. Kind of looks like a kite. Okay, but it's definitely not a kite. To be a kite, these sides would need to be equal and these sides would need to be equal. And obviously, one, it's not marked, and two, just by looking at it, you can tell that those are not all equal. So this is just a general quadrilateral. There's no specific name for this, but since the diagonals are hitting at 90 degrees, this new formula that we're going to look at here Area equals 1/2 times diagonal 1 times diagonal 2. So you're multiplying the length of the diagonals, not the sides, the diagonals. So from corner across to the other corner, corner across to the other corner, if they hit at 90 degrees, you can use this formula. Now, for our special quadrilaterals, we know there's 3 of them that do hit at 90 degrees, and it is a kite. Try and think back to that hierarchy that we had. What was underneath the kite was a rhombus, and underneath the rhombus was a square. So, if we're given a problem and they tell you that it's a kite, a rhombus, or a square, or there's enough information in the picture for you to know that it's a rhombus or a square or a kite, like all the sides are the same, or you've got sides like this, 2 equal sides, 2 equal sides, 2 pairs of consecutive sides, that's a kite. If they don't give you enough information or tell you that it's one of those 3 special ones, they also could just tell you that the diagonals hit at 90, and this formula still holds true. Now let's think for a second. For a square and a rhombus, those are parallelograms, and a square is a rectangle. And so your base times height is going to work, right? This could be kind of squeezed down where all 4 sides are equal. And it's just a rhombus at that point. A parallelogram can be a rhombus. And so you could use your base times height formula, but maybe you don't have the information on the sides. Maybe the only information that you're given is enough to talk about the diagonals. Well, now we can use this formula. So there are shapes that you can use more than one formula to solve, depending on what information is given to you. All right, so for example number 2, they just tell you this is a 4-sided shape. You can clearly see this is not a specific one like a kite or a rhombus, but they do tell you this information. AC is perpendicular to BD. Perpendicular means hits at 90 degrees. Once I see that, I know I can use this formula. Notice I'm not adding diagonals, I am multiplying. They're just next to each other here. They tell you that AC, which is a diagonal, is 40. So I'm going to plug that in. And it doesn't matter which one you call diagonal 1 and diagonal 2 because you're multiplying any order, doesn't matter. And BD, the other diagonal, equals 30. Notice those are not sides of the shape. They go across from vertex to vertex. That's your diagonal. If they hit at 90 degrees, I can use this formula. I have enough information, this is your basic problem, to just run it straight across. So half of 40 is 20. 20 times 30 is 600. So there's your basic use of that formula. All right, example 3, last one. Not everything is cookie cutter and given to you. Now, again, they don't tell you this hits at 90 degrees. So can I use that formula? The answer is yes, because I've got these markings here that tell me this is a kite, and I know that kites hit at 90 degrees here on the inside. So I can say area equals 1/2 diagonal 1 times diagonal 2. Because I have enough information to say that's a kite, which tells me that I have perpendicular diagonals, I can use that. Now remember, you could, if you had enough information here, just solve for the area of all 4 of these triangles or the 2 bigger triangles together and then add them up, and that would give you the same answer. So there are multiple strategies in these area problems that could work, and you want to make sure you know how to do all of them. So you would do 1/2 base times height for each one of these triangles, and then you would combine them to get your total area. But in this case, we can use the diagonals much quicker, much easier here because they are hitting at 90 degrees. So they tell you DO equals 15. And so that's not a full diagonal, so be careful. A lot of people would just plug that in. And then AC equals 25. Okay, and that is one of my diagonals. So I'll go ahead and plug the 25 in. For diagonal 1, AC is 25, but I need DB for this piece right here. And right now I don't have it. But if you remember back to your special properties of a kite, both of these diagonals are not bisected in a kite. That's a rhombus. I'm sorry, not a rhombus. That is isosceles trapezoid down to a rectangle down to a square. And a parallelogram as well. Oh, I'm all over the place here for that hierarchy. But what's important is the kite, yeah, this isn't bisected, right? We can just see that. And so you've got these two, though, that are going to be equal in a kite. So that's one of the special properties that we know is this diagonal gets cut into two equal pieces. So this one is also 15. And so all of this here is going to equal 30. And now I have the information. So be careful. Don't just grab the numbers you see and plug them in. Make sure that they are actually representing the two diagonals. In a kite, this diagonal specifically is bisected. They're not both bisected, but that one is. And so now I can run these numbers here. Now, half of 25, if I'm doing this mentally, is not, it's 12 and a half, but it's not a number that I want to be using for mental math. So I could take half of 30 and get 15 and do 15 times 25. Or, of course, you could just plug this all into your calculator and let it handle it. And so we are going to have 375. So again, a kite, this diagonal is bisected, not both of them. I misspoke. The isosceles trapezoid, they're not both bisected. They're both equal to each other. So back to that hierarchy real quick. The middle section where you have your parallelogram, those are the ones that are bisected. So underneath that, you've got your rhombus, your rectangle, and your square. And those are going to have both diagonals bisected. But a kite does have one, the one that is between these two unequal sides. Okay, so we've got that information there to help us figure this out.